Hey friends, welcome to the YouTube channel all about electronics. So in one of the earlier videos, we already learned about the analog comparator. So similarly, now let us learn about the digital comparator. So this digital comparator is also known as the magnitude comparator. So this magnitude comparator is the combinational circuit which compares the two n-bit numbers and it gives the output in form of the three status variables, that is A is equal to B, A greater than B or A less than B. And depending on the inputs at any given time, only one of the output is high. So now let us see the design of this digital comparator. And to understand the design, first of all let us start with the 1-bit comparator. So this 1-bit comparator compares the two 1-bit numbers. So first of all, let us see the truth table of this 1-bit comparator. So when we are comparing the two 1-bit numbers, then for the 2 bits, we have total 4 different combinations. And this is the truth table of the 1-bit comparator. So as you can see, when both the bits are same, then we can say that this A is equal to B. That means whenever both A and B are 0 or both A and B are 1, then we can say that this A is equal to B. So for this A is equal to B, if we see the logical expression, then that is equal to A bar dot B bar plus A dot B. And this expression is equivalent to the expression of the XNOR gate. That means using the single XNOR gate, we can implement this A is equal to B. Similarly, this A is greater than B when the number A is greater than B. And that is only happening when the number A is equal to 1 and B is equal to 0. So if we see the logical expression for this A greater than B, then that is equal to A dot B bar. And this is how it can be implemented using the logic gates. Similarly, this A is less than B when the number A is equal to 0 and the B is equal to 1. So if we see the logical expression for the same, then that is equal to A bar dot B. And this is how it can be implemented using the logic gates. And this is the overall circuit of the 1-bit comparator. So in this way, with the help of the truth table, we can design this 1-bit comparator. Likewise, in case of the 2-bit comparator, the each number consists of 2 bits. So overall if we see, then for the 2-bit comparator, we have total 4 different bits. That is A1, A0 and B1, B0. Let's say this A is equal to A1, A0 and B is equal to B1, B0. That means for the 4 different inputs, we have total 16 different input combinations. And this is the truth table for this 2-bit comparator. So as you can see, this A is greater than B when the A1, A0 is greater than B1, B0. And in this case, it is happening for the 6 different input combinations. Likewise, this A is less than B whenever this A1, A0 is less than B1, B0. And once again, it is happening for the 6 different input combinations. And likewise, this A is equal to B when both A1, A0 is equal to B1, B0. And as you can see, here it is happening for the 4 different input combinations. So for all the 3 outputs, with the help of the K-map, we can find the minimized Boolean expression. And with the help of it, we can find the logic circuit for each different output. And in fact, in the recent quiz number 394, we have already covered the similar type of question. So in this way, we can also find the logical circuit for the 2-bit comparator. But as you can see, as the number of bits increases, then the number of rows in the truth table will also increase. For example, for a 1-bit comparator, we have total 2 variables, that is A and B. So for the 2 variables, we have total 4 different combinations. Or in other words, in the truth table, we have total 4 rows. Similarly, in case of the 2-bit comparator, we have total 4 variables and in the truth table, we have total 16 rows. Likewise, if we go for the 3-bit comparator, then we have total 6 variables and the total number of rows in the truth table will become 64. Likewise, for the n-bit comparator, we have total 2n variables and the total number of rows in the truth table is equal to 2 to the power 2n. That means as the number of bits in the comparator increases, then the number of rows in the truth table will also increase. That means as the number of bits n increases, then it becomes difficult to make the n bit comparator using the truth table method. So in such case, we can use the another type of design. So this algorithm is very similar to the algorithm which we are using for comparing the two n bit numbers. So using the same technique, let us design the 2-bit comparator. So let's say the two numbers are a1 a0 and b1 b0. So in this technique, what we will do, we will start the comparing the two numbers starting from the MSB. So first of all, we will compare the MSBs of the two numbers. So if the MSB of the one number is greater than the other one, then we can directly say that the one number is greater than the other one. Now if both the MSBs are equal, then we should look for the next higher bit. So in this case, suppose if a1 is equal to b1, then we should look for the next higher bit, that is a0 and b0. So suppose if a0 is greater than b0, then we can say that the number a is greater than b. On the other hand, if a0 is less than b0, then we can say that the number a is less than b. And suppose if a1 is equal to b1 and a0 is equal to b0, then we can say that both the numbers are equal. So in this way, starting from the MSB, if we start comparing the two numbers, then we can easily find that which number is greater than the other one. So using this technique, we can easily design the n-bit comparator. So first, let us see the 2-bit comparator. So as I said, for a is equal to b, both the numbers should be equal. That means a1 should be equal to b1 and the a0 should be equal to b0. Now earlier, for the 1-bit number, we have already seen the logical expression for the equality, and that was equal to a XNOR b. So in this case, the logical expression for a is equal to b is equivalent to a1 XNOR b1 dot a0 XNOR b0. So here, this a1 XNOR b1 corresponds to a1 is equal to b1 and the a0 XNOR b0 corresponds to a0 is equal to b0. So this is the logical expression for a is equal to b. And if we see the logic circuit for the same, then this is the logic circuit for the a is equal to b. That means for the two 2-bit numbers, using this logical circuit, we can easily decide whether the two numbers are equal or not. Similarly, now let us see the logical circuit for the a greater than b. So as I said earlier, to decide which number is greater than the other one, we will start from the MSB. So if a1 is greater than b1, then we can say that the number a is greater than b. For example, let's say the number a is equal to 1 0 while the number b is equal to 0 1. So in this case, if we start the two numbers from the MSB, then the a1 is equal to 1 while the b1 is equal to 0. And since the a1 is greater than b1, so we can directly say that the number a is greater than b. Now it might happen that the MSBs of the two numbers can be equal. That means both a1 and b1 are equal. So in that case, we should compare the next higher bit. So suppose if a0 is greater than b0, then we can say that the number a is greater than b. For example, let's say the number a is equal to 1 1 and the number b is equal to 1 0. So to compare the two numbers, we will once again start from the MSB. So in this case, both a1 and b1 are equal. That means now we will move to the next higher bit. So in the next higher bit, this a0 is equal to 1 while the b0 is equal to 0. And since the a0 is greater than b0, so we can say that the number a is greater than b. That means for the two numbers, starting from the MSB, if we start comparing the two numbers, then we can easily decide which number is greater than the other one. And this is the logical expression for the same thing. So earlier, we have already seen the logical expression for a greater than b, and that was equal to a dot b bar. So in this case, for a1 greater than b1, the equivalent logical expression is a1 dot b1 bar. Similarly, for this a1 is equal to b1, the equivalent logical expression is a1 XNOR b1. And likewise, for this a0 greater than b0, the equivalent logical expression is a0 dot b0 bar. So in terms of the logical expression, the same thing can be represented like this. And using this logical expression, we can easily design the logic circuit. So this is the logic circuit for a greater than b. Likewise, now let us see the logical circuit for the a less than b. So once again, to compare the two numbers, we will start from the MSB. So if A1 is less than B1, then we can say that the number A is less than B. For example, if A is equal to 0, 1 and B is equal to 1, 1, then starting from the MSB if we compare, then this A1 is equal to 0 and the B1 is equal to 1. And in this case, since A1 is less than B1, so we can directly say that the number A is less than B. Now the second case is both MSBs are equal. That means whenever both A1 is equal to B1, then we should compare the next higher bit. So in that case, suppose this A0 is less than B0, then we can say that the number A is less than B. For example, let's say the number A is equal to 1, 0 and B is equal to 1, 1. So in this case, if you see, then both the MSBs of the two numbers are equal. That means to compare the two numbers, we should move to the next higher bit. So in the next higher bit, this A0 is equal to 0 while the B0 is equal to 1. And since the A0 is less than B0, so we can say that the number A is less than B. So in this way, we can easily decide which number is greater than the other one. And this is the logical expression for the same thing. So for the 1-bit number, we have seen that the logical expression for A less than B is equal to A bar dot B. So similarly, for this A1 less than B1, the equivalent logical expression is A1 bar dot B1. Likewise, for the equality, we will use the XNOR operation. And likewise, for this A0 less than B0, the equivalent logical expression is A0 bar dot B0. That means this is the overall logical expression for A less than B. And using this logical expression, we can easily design the logic circuit. So for the 2-bit number, this is the equivalent logic circuit for A less than B. And if we combine all the three circuits together, then this is the overall circuit for the 2-bit comparator. So in this way, we can design the 2-bit comparator. Similarly, let us see the design for the 4-bit comparator. So for the 4-bit comparator also, the algorithm will remain the same. So first, let us see the logical expression for A is equal to B. So we can say that the two numbers are equal when all the bits of the two numbers are equal. And if you see the logical expression for the same thing, then this is the logical expression for the A is equal to B. That means using the 4 XNOR gates followed by the 4 input AND gate, we can design the logic circuit for the A is equal to B. Similarly, now let us see the logic circuit for A greater than B. So once again, to compare the two numbers, we will start from the MSB. So if A3 is greater than B3, then we can say that the number A is greater than B. Now the second possibility is the MSBs of the both numbers are equal. So in that case, we will move to the next higher bit. And while comparing the next higher bit, if this A2 is greater than B2, then we can say that the number A is greater than B. Now it might happen that starting from the MSB, the first two bits of the two numbers are equal. So in that case, we should compare the next higher bit. So while comparing, if this A1 is greater than B1, then we can say that the number A is greater than B. And in the last case, it might happen that starting from the MSB, the first three bits of the two numbers are equal. So in that case, we should compare the LSBs of the two numbers. So if this A0 is greater than B0, then we can say that the number A is greater than B. And this is the logical expression for the same thing. So here, this A3.B3 bar represents this A3 greater than B3. Likewise, this A3 XNOR B3 represents this A3 is equal to B3. And similarly, this A2.B2 bar represents this A2 greater than B2. And likewise, we will have the other two terms. So similarly, now let us see the logical expression for A less than B. So to find the logical expression, once again, we will start from the MSB. So whenever this A3 is less than B3, then we can directly say that the number A is less than B. Now if the MSBs of the two numbers are equal, then we should move to the next higher bit. And in that case, if this A2 is less than B2, then we can say that the number A is less than B. Then the third case is both A3 A2 are same as B3 B2. So in that case, we should compare the next higher bit. that is A1 and B1. So if this A1 is less than B1, then we can say that the number A is less than B. And the last case is both A3, A2, A1 are same as B3, B2, B1. So in that case, we should compare the LSBs. So if this A0 is less than B0, then we can say that the number A is less than B. So in this way, starting from the MSB, if we start comparing the two numbers, then we can easily decide which number is greater than the other one. And this is the logical expression for the same thing. And of course, using this logical expression, we can also design the logic circuit for the same thing. So this is the overall logic circuit for the 4-bit comparator. So if I just zoom in this circuit, then this portion of the circuit decides when the both numbers are equal. So as you can see, using the 4 XNOR gates followed by the AND gate, we can design the logic circuit for A is equal to B. Similarly, this portion of the circuit decides when the number A is greater than B. And similarly, this portion of the circuit decides when the number A is less than B. So let me just zoom in the portion for A less than B. So as you can see, for the 4-bit comparator, we require the 5 input AND gate as well as the 4 input OR gates. So in general, if we design the AND bit comparator, then we will also require the N plus 1 bit AND gate as well as the AND bit OR gates. So as the number of bits in the comparator increases, then the number of inputs of the AND and the OR gate will also increase. So if you want to compare the two numbers which is more than 4 bits, then we should cascade the 4-bit comparators. And for that, we can also use the readily available comparator ICs. So one such IC is 7485. So this 7485 IC is the 4-bit comparator. So as you can see, for the 4-bit comparison, it consists of the 8 inputs and the 3 outputs. And of course, apart from that, it has the 2 pins for the VCC and ground. Moreover, it also consists of 3 more inputs. That is A greater than B, A is equal to B and A less than B. And these 3 inputs are useful when we are cascading the multiple ICs. But when we are using the single IC, then we should keep this A is equal to B input high. Well, why we should keep that high, it will get clear to you very shortly. But using this IC, we can compare the two 4-bit numbers. So when the number A is greater than B, then this output A greater than B will become high. Likewise, if both numbers are equal, then this A greater than B output will become high. On the other hand, when the number A is less than B, then this last output, that is A less than B, will become high. So in this way, using this 7485 IC, we can easily compare the two 4-bit numbers. Moreover, by cascading multiple such ICs, we can also compare the AND bit numbers. For example, just by cascading the two such ICs, we can compare the 8-bit numbers. So as you can see, the IC on the left hand side compares the LSBs, while the IC on the right hand side compares the MSBs of the two numbers. And here, the output of the one IC is given as an input to the next IC. So as you can see, this A greater than B is equal to B, and the A less than B outputs of the LSB IC is given as an input to the next IC. So whenever this number A7, A6, A5 and A4 is greater than this B7, B6, B5 and B4, then this A greater than B output of the MSB IC will become high. On the other hand, if the MSBs of the number A is less than the number B, then this A less than B output will become high. But suppose if MSBs of the both numbers are equal, in that case, this IC will look for these 3 inputs. Or in other words, in that case, it will look for the output of the LSB IC. So while comparing the LSBs of the two numbers, if this A is greater than B, then this output will become high, and the same will be available at this input. So in that case, based on this input, the A greater than B output of this MSB IC will become high. On the other hand, if this A is less than B, then this last output will become high. And if A is equal to B is high, in that case, this A is equal to B output of the MSB IC will become high. So in short, these 3 inputs will come into the picture when all the 4 bits of the two numbers are equal. And in that case, the MSB IC will decide based on the preceding output. On the other hand, whenever we are using a single IC, then this A is equal to B input should be kept high. Of course, these three inputs won't come into the picture when the number A is greater than B or A less than B. But it will come into the picture when both the numbers are equal, because in that case, the comparator IC will look for these three inputs. So to get the correct output, this A is equal to B should be kept high. So when all the 4 bits of the two numbers are equal and this A is equal to B input is high, in that case, this A is equal to B output of the IC will become high. And in this way, we will get the correct output from the IC. So in this way, by using this standalone 7485 IC, we can compare the two 4-bit numbers, or by cascading such ICs, we can compare the n-bit numbers. So I hope in this video, you understood the concept of the digital comparator. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe the channel for more such videos.